Thank you, Renji. I appreciate it very much. Great job today. And I'm trying to share my screen. I'm not sure if it's there. Is it there? Good. Thumbs up.
Yep.
All right, great. So I want to say thanks to all of our speakers today. I mean, this was another great session, great presentations. I think underscoring the importance of technology, but also human behavior and decision-making for individuals, for school districts, et cetera. You can have great technology, which is worthless if it's not used. And you can have poor technology and it's worthless even if it is used. And so, you know, a lot of great things coming out from this workshop. We had 19 presentations in this workshop, 12 hours of sessions, over 500 slides, I believe. And somehow I'm going to try to summarize all that in 15 minutes. So I'll do my best and try to hit some of the high points. The system we're dealing with is complex. I mean, that's one thing that kind of came out from the 12 hours of workshops. You know, we have PM 2.5 of outdoor origin mixed with PM 2.5 generated indoors. There's transformations that occur indoors. Ventilation is an important defining factor, deposition of particles onto surfaces, engineered controls. It's important to understand exposure of occupants and the inhalation dose and where particles go in the respiratory system and what the health effects are. There's significant temporal variations for sources and indoor concentrations of PM 2.5. There's also significant spatial gradients, both outdoors and indoors. There's differences in how occupants perceive indoor air quality and how they behave and how they respond, and there's differences in policies. And then there's socioeconomic status issues that are superimposed on all of this. This underscores the fact that we need an interdisciplinary approach to deal with these problems. And even though the system is complex, one of the nice things about this workshop is that there were some really practical nuggets that came out, and I'll try to highlight some of those. We'll start with outdoor sources of PM 2.5. There are many. I don't need to go through all of these. But again, there's significant temporal variations and spatial gradients with respect to outdoor sources of PM 2.5 that affect indoor PM 2.5. And there are significant environmental justice issues associated with the locations of underserved communities with respect to many of these sources. There's the outdoor to indoor transport of PM 2.5 across the building envelope. Brent Stevens spoke about the fact that the infiltration factor for PM 2.5 that's outdoors coming indoors has a central tendency about 0.5, although it varies a lot by specific homes and by city and by season, but the central tendency about 0.5, which means that about concentrations of particles indoors that are of outdoor origin are about half of what they are outdoors. And there are a lot of major factors that affect that. There was an interesting analysis done of microenvironmental PM 2.5 exposures that suggested that about 71% of our exposure to PM 2.5 occurs in our homes and about 20% inside other buildings. So by difference, you can see how much happens outdoors, less than 10%. And of our exposure inside these buildings, roughly half is to PM 2.5 of outdoor origin and half is to PM 2.5 of indoor origin. These are generalizations again, but good to keep in mind that our exposure indoors is to both outdoors and indoor PM 2.5. There are indoor sources of PM 2.5, and I list a lot here by category: combustion, which involves cooking and candles and fuels; phase change, we heat up oils, they get driven into the air where they're cooler and they condense; mechanical, like ultrasonic humidifiers and vacuum cleaning; biological, respiratory aerosols and mold spores and that kind of thing. Chemical reactions can occur indoors that generate secondary organic aerosol, and with a wide range of products, including secondary organic aerosols. And then we heard from Nina Vance in the first session about cooking and emissions from the heat source, from oils that are used from cooking, from the food itself. Without exhaust, we could be talking about hundreds of micrograms per cubic meter during cooking. Particle number is dominated by the fuel source, and emissions and composition are highly variable during cooking events, and there's very little information about what that means with respect to health. All right, so transformations occur in indoor atmospheres. When outdoor PM 2.5 comes indoors, they see a large surface to volume ratio that they didn't see outdoors, if you can put human qualities to particulate matter. see less oxidants, a lot of VOCs and semi-vol organic compounds indoors, much higher concentrations than outdoors. Evaporation occurs, which can shrink particles. Thermal partitioning occurs, which changes the composition of particles. There's uptake of SVOCs like plasticizers indoors. And these transformations can be quite significant. They can affect size, pH, chemical composition, et cetera. And those transformations occur for particles of outdoor origin and indoor origin. So one question is do these transformations of particles change the particle health effects? We actually don't have good data on that at the moment. Effects of relative humidity on PM2.5. We know that relative humidity affects water content of PM2.5, which can change the size of particles, especially for particles like respiratory particles. Can also affect chemistry that happens in those particles and microbiology that happens in those particles. We know that bacteria survival is lowest at low RH, and virus survival is lowest at mid RH. So differences in whether we're talking about bacteria or viruses. And so one question is, what are the optimum environmental conditions we should have indoors to reduce the health impacts of PM2.5? Health effects of indoor PM2.5 was session 2. There's a lot of epidemiological studies on outdoor PM2.5. You can see the annual mortality rates here in the United States. Most of the effects that are observed are cardiovascular effects when we focus on outdoor PM2.5. But remember that the indoor dose of PM2.5 of outdoor origin is about 70% of the total dose. Howard Kippen presented a quick calculation to show that in our second session. And I think his comment was outdoor epidemiology when it comes to PM2.5 is indoor epidemiology when we're looking at particles of outdoor origin. We know that increases in indoor PM2.5 have been associated with increases in asthma and COPD morbidity. Meredith McCormick spoke about that in our second session. And reduced PM2.5 with portable HEPA filters does reduce symptoms. Andrea Farrow in the first session mentioned that there are some limited studies with mice and rats that show that indoor PM2.5 has greater toxicity than outdoor PM2.5 with respect to inflammatory and cytotoxic effects, but also acknowledge that there's a very limited number of these studies and more research is needed. There's a complexity of assessment of metrics for indoor PM2.5. It's better to measure indoor particles than outdoor particles and try to predict what happens with outdoor particles. Personal measurements are best if we can make them, but they're cumbersome. There are 4 dimensions to complexity associated with indoor PM2.5. We have a broad size range, even within the PM2.5, from ultrafine all the way up to 2.5 microns. Chemically complex particles, high temporal variability in concentrations, and spatially variable. And I think Bill Nazaroff made the comment that no instrument measures everything. So one question is, what measurements are the most important? And where should we make them? And when should we make them? Right? There's still optimization to be done there. There's complexity of measuring actual exposure to PM2.5. Do we focus on short time scales like hours or longer time scales like months? Depends on whether we're looking at acute or chronic health effects. Time between exposure and onset of health impacts is important. And there are substantial differences that Kirsten Kohler showed in session 2 by person, by day, for the same person, by day. But our exposures tend to be dominated inside our homes. Inhalation dose and location in the respiratory system are both important. How do we improve our ability to more easily measure or estimate exposure? Still work to be done there. Low-cost consumer instruments for PM2.5. There's growing use of these instruments, these optical instruments, but protocols are lacking. There are a lot of different metrics that are used to compare them against reference instruments and look at limits of detection and that type of thing. In the laboratory, under controlled laboratory conditions relative to reference instruments, these devices tend to be plus or minus a factor of 2, but worse than that in the field with a lot of conflicting factors. There are problems with these devices when we get to concentrations less than 10 micrograms per cubic meter, which is actually a fairly common range for PM2.5 indoors. They can be applicable to trends to see that things are going up rapidly or down rapidly to tell us something bad's happening or something better is happening if we put on a portable HEPA air cleaner, et cetera. And how do we best use these to improve indoor air quality during wildfire season and that type of thing? I combined here some of Lindsay's comments, Lindsey Graham, with Dusan Lachina's. And I think moving forward with these low-cost sensors, we have to understand that individual perception of indoor air quality is important. And can sensors help with those perceptions? Lindsay presented information that suggested that anything that gives healthy action visuals is preferred to people. They don't want to just have a number that says 12 or 20, right? Clear, graphical, and actionable information is important. Providing steps to individuals to overcome poor indoor air quality. And I added this last point is, do we need an indoor air quality Alexa that goes along with these things that says, you know, turn on the exhaust vent, Carl, you know, kind of thing. Let's see. Mitigation of indoor PM 2.5 was a main point of our session today. Improve filtration, and these are points made during the health session, so day 2. Improved filtration has been associated with subclinical cardiovascular benefits, increased birth weight, reduced asthma morbidity, and higher test scores in schools. And then portable HEPA air cleaners have been associated, especially in homes of children with asthma, with substantial reductions in PM 2.5 and an increase in symptom-free days for children with asthma. And that general response is supported by some of the modeling that Stuart Batterman showed today. But these studies are really limited in number, and we have to do better at communicating the benefits of improved filtration. And then, as was mentioned today by Sarah, you know, can we get to the point of actually developing standards to help people? Mitigation of indoor PM 2.5 by local exhaust. So Brett Singer today spoke about emissions from cooking, and as did Nina Vance on day 1. Local exhaust of cooking emissions can be done with a range hood, downdraft exhaust, ceiling or wall exhaust, or open window. Hood capture efficiency is important. It increases with airflow. It's best when back burners are used, and I was struck by some of the data that Brett showed today of what a huge impact that has on using back burners as opposed to front burners. Again, how do we communicate that to the public? And then outdoor exhaust is important, not just recirculating back into your face. And it's extremely retrofit. It's extremely expensive to retrofit if you don't already have that. And again, just like with any technology, all of this is irrelevant if somebody doesn't use their exhaust vent when they're cooking. So occupant behavior is important. Most use their hood in the study that Brett mentioned less than 50% of the time while cooking. Can we use sensors to help with, you know, telling people, whether they be visual sensors on the hood or verbal reminders from Alexa, or can we basically make it automatic that fume hoods come on when anybody is cooking? And then can we make those hoods quieter, which seems to be an issue with people. In terms of filtration, in air handling units, Jeff Siegel gave a great presentation on the importance of effective filtration, which means good filter, properly installed, large enough flow, large enough runtime, replacing the filter frequently, making sure you don't have bypass, et cetera. And then the issue of other cleaning technologies came up, which are not well defined, lacking independent evaluation, and potentially harmful for some of these unproven technologies. They're getting a lot of look right now. Earlier on day 2, I think it was Stephanie Holm mentioned that anions from ion generators have been associated with markers of inflammation in adults and decrease in heart rate variability in children, which is not a good thing. In terms of schools, Elliot Gall made a nice presentation where he suggested that 15% of US schools are within 250 meters of major roadways. So this is another environmental justice issue for many schools near roadways. Traffic-related air pollution does impact asthma and cognition. Elliot measured black carbon ultrafine particles PM 2.5 and found them in a school in Portland, Oregon to be substantially above urban background, and found significant reductions in all of these, particularly PM 2.5, with MERV 8 pre-filters followed by MERV 16 filters, and also found significant quenching of secondary organic aerosol formation, which I mentioned earlier to be another source of indoor particles by using activated carbon to remove ozone and unsaturated organic compounds that ozone reacts with. So opportunities to reduce PM 2.5 for schools, increase distance from the roadway, alter the time of activities of children outdoors to not be at heavy roadway times, traffic times, maybe alter ventilation to have less ventilation in the morning when you have substantial traffic nearby, employ effective filtration, reduce indoor sources, and quench chemistry. And getting close to the end here, Stuart today talked about portable HEPA filters, found significant removal, 50 to 80% of particulate matter reduction in bedrooms of children with asthma in inner cities. I think it was in Detroit. There was a field study that he did involving a large number of homes and found a significant drop-off in use of the HEPA filters over time. There were significant differences in use by household, but in general, a big drop-off. There were perceptions of energy costs, even though I think in this study that was being paid for, part of the study. There are questions about measurable health benefits, which is, I think, an area for more research, but modeling suggested a reduction in asthma burden using the use of HEPA filters. A proven technology. It's particularly valuable when you have lower air exchange rates. Smaller units that are less noisy and less drafty seems to be something that people would like. User feedback on the benefits with the system, again, getting back to maybe sensors is important. And then, perhaps improve controls so that these things switch on by themselves if somebody's in the room. Variations of indoor PM 2.5 for wildfires. Sarah gave a really nice presentation today on the practical impacts of trying to protect people from wildfire smoke. And there were a number of factors in her presentation that suggested things that increase indoor PM 2.5 of outdoor origin during wildfire smoke. Most buildings are using MERV-8 filtration. There's a high variability in PM 2.5, even in buildings that have the same MERV-8 filters. HVAC maintenance is critical. To reduce exposure, messaging is critical, and that's something that Sarah hammered over and over and over again. And we heard a lot during our workshop. Preparation is critical. Don't wait until the wildfire is in full bore. Prepare beforehand. Control ventilation, increase filtration. Again, the use of portable HEPA air cleaners can be very valuable during wildfires, and we do need to think about more policy level standards here. So a lot of opportunities here for trying to reduce population exposures to PM 2.5 during wildfires and other events. And as was mentioned by Sarah, funding is an important factor if states and communities are going to be able to help. Last slide. Economic disparities are very important. This was a thread throughout our workshop. There's substantial exposure and health disparities related to socioeconomic status and PM 2.5. Underserved communities really carry a high burden in here, and they should be a high priority in everything that we do. They tend to have greater proximity to outdoor sources, which means more PM 2.5 of outdoor origin indoors. Physical structure of residences is important. In lower SCS communities, oftentimes the size of the home is smaller, meaning higher concentrations of pollutants from a given source. Occupant density tends to be higher. You see a lot of multifamily as opposed to single family homes. The nature of ventilation and local exhaust sometimes doesn't exist in lower SCS communities. The time spent in the home can be quite a bit higher. Cooking practices. We heard about the use of wood and coal for cooking in Southeast Kentucky and increased asthma symptoms in that part of the world. Smoking and smoking-related diseases tend to be greater for lower socioeconomic status communities. Increased PM 2.5 is associated with asthma morbidity, and it's worse with obesity and poor diet, which tends to be higher in many communities that are of lower socioeconomic status. And of course, there's significant economic barriers, as Stuart just mentioned in the last Q&A session, to being able to even have control systems in these communities. They're expensive. $250 is a lot to many families. So that is my summary. I want to close by acknowledging again the US EPA's Office of Radiation and Indoor Air, Director Jonathan Edwards, and to Laura Cobb of the Indoor Environments Division for great guidance when we kicked off this workshop. I want to thank the National Academies, David, Guru, Kathleen, Courtney and Michael, great job helping us along the way. 19 wonderful presenters. I'm not going to list them all, but just great presentations all 3 days. And and I also want to thank the workshop planning committee, which I did at the beginning of this session. But again, I can only say that everybody on this list spent a lot of time discussing who our speakers should be and the flow of the presentations. And I think it worked wonderfully. So thank all of them. And thank everybody who tuned in today into all of our sessions. This was really about all of you. And I just appreciate it very much. And I'll end there.